Hello everyone and welcome back again. Today we're going to talk about gas density and I'm going to show you two things in this video. The first one is how to derive the formula for calculating the density of a gas, and secondly I'm going to show you how to solve these two problems right on your screen. Now let's dive right into it. The formula for gas density is giving us density equals pressure multiplied by the molar mass and divided by the ideal gas constant and multiplied by temperature. Now, the question is, where does this formula come from and why is it important that we know how to do it? So sometimes your lecturer might not want you to just begin with this. He or she might want you to derive the formula first before you can start plugging in and solving the problem. Now, where does it come from? D equals PMR over ROT. This formula comes from the ideal gas equation, which is PV equals nRT. Now, you might be wondering, what is the relationship between PV equals nRT and D equals PMR over ROT? Now, let's begin with the derivation step by step. Remember that this P refers to pressure, the V refers to volume in liters, N refers to the number of moles of gas, R refers to the ideal gas constant, and then T refers to the temperature in Kelvin. Now remember that moles, I'm going to say recall, N, which is moles, equals mass over molar mass, okay? Which is known as MR. Okay, our moles equals mass over molar mass. So this implies that we say N is equal to M over MR. So wherever we see N, we simply replace it with mass over molar mass. Now let's do that. Here we have PV is equal to, doing the replacement now, we have M over MR. Then this is multiplied again by RT. Now we have a fraction right on the right hand side. How do we remove this MR from here? We simply multiply both sides by MR. Okay, so this MR will be distributed across everything inside the bracket. We want to remove this. So we now have PV MR. When you distribute the MR, so the MR goes to the PV, it also goes with this one. Now when you multiply MR by this, you now have this is equal to MR then multiplied by M over MR. Okay, and then we're still multiplying this by RT. Mathematically, this MR can cancel with this one here. And what are we left with? We have PV MR equals MRT. Okay, now remember we're looking for density, right? We're looking for density. So what we do right here is that we know that density is equal to mass over volume. And luckily we have volume here. We also have mass here. So we simply divide both sides by volume. Divide both sides by V, divide both sides by V. This V cancels out with this, and we are left with P MR is equal to, now I'm going to rearrange this, okay, to be M over V, then multiplied by ROT. Now you might be concerned, why did I assign the V only to the M? Well, all these terms are multiplying, so mathematically you can rearrange them. So let's look at this way. Okay, so if the M multiplies the ROT, we still have our MROT back. And if the V multiplies the 1 here, you still have V back. Okay, so this can be written as ROT over 1. Any number divided by 1 is still the same number, or anything divided by 1 is still the same thing. And in this case, V times 1 still gives us our V. So we'll still get the original expression back if we decide to expand it back. Now let's now simplify. We should remember that density is equal to m over v, right? Now what do we have here? M over v. So we're going to replace this m over v that's inside this bracket with density. This now gives us the pressure multiplied by the molar mass equals density multiplied by RT. You can see we already have our density here. And what do? We divide both sides by RT to isolate density. Here we have RT. These RTs, they cancel out. We now have that density is equal to pressure multiplied by the molar mass over RT. Now this is a formula for solving for gas density. Okay, now why did I do all this? It's because sometimes the lecturer might not want you to use the formula without deriving it. Now you know how to derive it. Let's now go ahead and solve the problem. Let's solve the question together. Here we have the first question, which relates to gas density, and this is oxygen at 15 degrees Celsius and 655 millimeters of mercury. Now let's write our data. So we are given, we have O2 gas. So this is O2, which is oxygen gas. And then we are given our temperature to be 15 degrees Celsius. So you must always convert your temperature from Celsius to Kelvin, because this temperature here is in Kelvin. So you must always convert to Kelvin. So you just add 273, and then this is gonna give you 273 plus 15 should be 288. So this gives us 288 Kelvin. Okay, for the pressure, we were given 655 mmHg, which is 655 millimeters of mercury. So you must always make sure that your pressure is in units of ATM. You must always make sure that your pressure is in units of ATM. So we have to convert this 655 mmHg to ATM. Now what do? We say in 1 ATM, we have 760. This is the conversion factor, mmHg. So we basically convert. So we're looking for the value of 655 mmHg in ATM. So we use the chain link method where we say 655 mmHg times, which one are we looking for? We're looking for ATM. So we say in 1 ATM, we have 760 mmHg. Okay, so we basically set them up in a way that they're going to cancel out. This mmHg cancels out with this mmHg, and then we can multiply. So we have 655 times ATM, then over 760. Remember, we've cancelled out the mmHgs. So let's now divide 655 divided by 760. This is giving me 0.862. So this is equal to 0.862 ATM. Now we've converted this. The next one is to find the molar mass. Remember that here we have a pressure. In ATM, we have the molar mass. We have the ideal gas constant, which is a constant value. And we have our temperature. So all we're looking for right now is the molar mass. So we're going to use the atomic mass unit of oxygen to find the molar mass. Remember that we're dealing with a gas. And this is a diatomic molecule. So we say O2. We know that the atomic mass unit of oxygen is 16. So this now gives us 16. How many oxygen atoms are here? There are 2. So when we multiply them, we get 32 grams per mole. You may be wondering, how did I get the 16? This is from the periodic table. So you find it right there on the periodic table. Okay, now we found everything. Let's plug in and start solving. Okay, so for the ideal gas constant, our R is 0.08206 liter dot ATM slash mole Kelvin. Okay, now you've seen why your units of temperature must be in Kelvin, and then your volume must also be in liters. Finally, your pressure must always be in atm, because this R carries all this. So you must make sure that the units match. Now let's substitute. We have our D equals P mR over RT. Okay, so what's our pressure? Our pressure, we got it to be 0. Let me verify. 862. So we have 0.862. This is multiplied by the molar mass of oxygen gas, which is 32, and then over the ideal gas constant is 0.08206. And this is multiplied by the temperature, which we found to be 288. Okay, so let's work this out and see what we're going to get. So when you multiply 0.862 times 32, we have 27.584, 27.584 over, and then for the denominator, we have 0.08206 times 288. It's giving me 23. We have 23.633. Now when you divide the two of them, let's see, we have 27.584 divided by 23.633. We have 1.17. So the density is equal to 1.17. And what are the units? Grams per liter. Okay, so you must always make sure that your units are in grams per liter, because that is the appropriate unit for gas density. So we say density for this is 1.17 grams per liter. Okay, now we're done with the first question. We're going to solve the second one without having to derive the formula again. So the second question says that we should calculate the density of sulfur hexafluoride at 150 degrees Celsius and 25.0 atm. Okay, now luckily our pressure is in units of atm, but then our temperature is in units of Celsius. So that simply means that we have to convert from Celsius to atm. We also need to find the molar mass of sulfur hexafluoride before we can proceed to solve the question. So let me use another page. This is question 2. The chemical formula for sulfur hexafluoride is SF6. So we have 6 atoms of fluorine and 1 atom of sulfur. Again, we're given our temperature to be 150 degrees Celsius, and then our pressure was given to be 25.0 atm. Okay, now let's solve this question together. We have to convert 150 degrees Celsius to units of Kelvin. So we simply say 150 degrees Celsius plus, just add 273, and when you add 150 to 273, what do we get? Okay, let's check it out. 150 plus 273. So we have 423, so we say 423. Again, we have our pressure in units of atm, so that's correct. But then we need to find the molar mass of sulfur hexafluoride. So the first one I'm going to say for the molar mass. For the molar mass, we have the first one is sulfur. So on the periodic table, the atomic mass unit for sulfur is 32.06. 32.06. So we say 32.06. And then for fluorine, the atomic mass unit is 18.998. 18.998. Okay, so we then have to add them together. Since this one is F6, you have to multiply this one by 6. So we say sulfur is equal to 32.06. Okay, and then for fluorine, F6, this is equal to 18.998, and then we have times 6. So when you multiply 18.998 by 6, we have 18.998 times 6. This gives me 113, okay, 0.988, or we can say 113.99. That's still okay. So we have 113.9, okay, let's use 988, that's okay. And then we just have to add them together. So SF6 is equal to, here we have 32.06, then plus 113.988. So let's add them together, 32.06. So this gives me 146.5. We have the molar mass of SF6 is equal to 146 points, we can say 0.5, yeah, 0.5. 0.5 grams per mole. Then let's now go ahead and solve. So we say gas density is equal to pressure multiplied by the molar mass over, again we have our RT. Let's substitute. The pressure, we got it to be 25.0. The molar mass is 146.05. Then this is over our ideal gas constant is 0.08206, and this is multiplied by the temperature of 423 Kelvin. Okay, now the units are consistent. Let's go ahead and start solving. So the density equals, when you multiply 25.0 times 146.05, we have 3651.25, and this is over the denominator, which is 423 times 0.08206. So I'm getting 37, or 34 rather, 0.711. Okay, now let's go ahead and divide them to see what we're going to get. We have 3651.25 divided by 34.711. Okay, so I'm getting the density of sulfur hexafluoride at this temperature equals 105.2 grams per liter. And this is the solution. I hope you enjoyed this lesson. See you in the next video, where we're going to be talking about gas stoichiometry, Graham's law of effusion, and some other concepts like Dalton's law of partial pressures. Thank you so much for being there, and see you in the next video.